Welcome to week 2 lecture 1. We start from product ciphers. Idea of forming products of crypto systems is due to Shannon. Now, we know that a crypto system can be specified by P, C, K, E and D, where P is the set of plain text, C is the set of cipher texts, K is the set of keys, E is the set of encryption functions and D is the set of decryption functions. Now, we consider for simplicity the situations where P is equal to C, and we consider a cipher crypto system S1, which is denoted by P, then K1, the set of keys for S1, E1 and D1. We consider another crypto system S2, which has the same plain text and cipher text sets, and these sets are equal. Then we have K2, then E2 and D2. According to Shannon, the product of these two crypto systems S1 and S2 is written as S1 cross S2, and we have a crypto system P K1 cross K2. By this K1 cross K2 we mean the Cartesian product of the set K1 and K2. That means that it is a set of all ordered pairs of keys, first one coming from the key set of the first crypto system and the second one coming from the key set of the second crypto system, and then we have E and D, which we will have to define. So, we see that S1 cross S2, which is a product of S1 and S2, that is PP and then K1 cross K2, then E and D. Now, the question is that how we define E and D, which is given in the next slide, this one. So, encryption and decryption of product cipher. So, we have to know how to define E and D. In the case of individual ciphers S1 and S2, the encryption functions were like this: EK1 belonging to E1 and EK2 belonging to E2, whereas the corresponding decryption function dk1 belongs to D1, and dk2 belongs to D2. Now, we have a combined encryption function for the product cipher. We call the ordered pair of the keys as K. So, that is K1 comma K2, and the encryption function is labeled by K, which is the ordered pair K1 K2, and it operates over X, the plain text P, plain text in P. So, it is X, and then we have a sequence of functions, the first one coming from E1, that is EK1 applied over X, and then EK2 applied over EK1X. So, this is the result of the operation of EK1 K2 over X in the product cipher S1 cross S2. Now, the question is that what is the decryption function? The decryption function D, again K1 K2 applied over Y, will be equal to dk1 applied over dk2 y, where y is an element of C, that is the cipher text, and in this case C and P are same. Now, we know that if we apply encryption function over a plain text and we apply the decryption function with the same key over the cipher text generated from that plain text, then we should get the plain text back. Now, we have to check whether that property holds for this new definition. So, let us see. Suppose I take d k1 k2 applied over E k1 k2 x, then by using this rule I can write d k1 k2 applied over E k2 of E k1 x. Now, we use the second rule. Now, the argument of the decryption function is this sequence of encryption functions. Therefore, we will write d of k1 applied over d of k2 applied over E k2 E k1 x. I close a bracket, I close the other bracket, I close the last bracket. Now, look at this one. Since S2 is a cipher system or a crypto system, we know that dk2 ek2 x is equal to x for all x in P. Therefore, when dk2 is applied over ek2, I know that I will get this argument back, and therefore, I will get dk1 applied over ek1 x, and then since S1 is a cipher system, I know that dk1 ek1 x equal to x, and therefore, I will get x. Thus, we have this result that dk1 k2 ek1 k2 x gives me x for all k1 k2 and all x, and therefore, we see that we indeed have a crypto system. Now, an example of a product cipher is a combination of multiplicative cipher and a shift cipher, and we will see that if we take a multiplicative cipher and product it with a shift cipher, then we get our affine cipher. Now, let us look at this. A multiplicative cipher is something easier than affine cipher. We have got P and C both equal to Z sub 26, and the set of keys is all numbers co-prime to 26 as I have written over here, and the encryption function is just multiplication modulo 26 with a chosen key. In this case it is A, and decryption is done by taking A inverse and multiplying to the cipher text modulo 26. So, this is a multiplicative cipher, and now we know that we have the usual shift cipher, and let M be the multiplicative cipher that we have seen just now, and usual shift cipher is just to add the key modulo 26 to the plain text between 0 to 25. If we take the product S cross M, then we will get affine cipher. I will quickly show this result, and I will ask you to check this in more details after the class. So, we take the multiplicative cipher M, P and C both are Z sub 26 and the key let us call it Km, which is equal to all A belonging to Z sub 26 such that GCD of A and 26 is equal to 1. Now, for the shift cipher, P is equal to C is equal to Z 26 and Ks, which is the shift cipher, the key set, that is equal to K, an element of Z 26, any element of Z 26. All right. So, if I am taking S cross M, then according to the definition, P will be Z 26, C will be Z 26, that is all right, and the keys will be Km, Ks cross Km, and then I will have the encryption function and decryption function. So, now let us see the encryption function. So, the encryption function of M, that is EA of x is equal to AX mod 26. Now, the encryption function of, let us superscript it with M to indicate that this is the encryption function of the multiplicative cipher. Then for the shift cipher, the encryption function ES on x is going to give me x plus k with the key k is going to give me x plus k mod 26. And now, if I apply EAM on EKS like this over x, I will get EKS, and here I will get AX mod 26, and this is going to be AX plus k mod 26, and this is exactly the encryption function of the shift cipher, the encryption function of the affine cipher with the affine cipher. Yeah. So, it is the encryption function of that. Now, only thing that we will see is that here the key set is turned in a way, turned the other way round. In the case of affine cipher, we write the key space as this: A comma B Z 26 by Z 26, where A 26 GCD is equal to 1, which is equal to Km cross Ks, but in this case I have got this Ks cross Km, but that is not going to be a big problem because they are essentially the same set. All right. Now, there is a question: are these two sets S cross M, M cross S, I am sorry, are these two crypto systems same? Now, this question I leave as an exercise please try to prove it whether these two crypto systems are same, and the answer is yes, they are same, but it needs a proof. Now we move on to block ciphers. The idea of block cipher is based on product ciphers and on something more specifically a iterated product cipher. So, we have a particular cipher which we keep on applying over a plain text iteratively several times, and in the process get something which is called a block cipher. It is called a block cipher because it is applied over a block of plain text, or a block itself is called the plain text. In more particularly, we will be taking a 64-bit segment and call it a block, and we will apply our transformation of the crypto system on that 64-bit block, or it may be a 32-bit block or something like that, but it will be a block. And we will essentially apply a simple transformation over and over again, and then that will result in security. Now, there are some terms which are used in the context of block ciphers very frequently. So, each iteration is called a round. Each round involves one round function and a round key which is obtained from a key schedule specified to the cipher. Now, it is like this, that we will have a key, a kind of master key which is in the key space, and from this key we will generate a key schedule of this type, maybe some kn. I have to see what we have written in the slides, but so it's called some kind of sub key or round key or something like that, and we will have a round. Right now I am writing it as a box. So, we will have an input, let us say x, and it is a first round. So, first sub key or first round key will go here. We will somehow combine these two things. So, I will have a function gx which will gx k1, a function g which combines x and k1 and gives me something, let us call it w1. Then this w1 will be passed to the next round. It is an iterative cipher. So, usually it is the same function. So, applied over w1 with the round 2 key. So, it is w2, it will again pass on to the next round and so on. Ultimately, it will come to the last round and it will give me the final enciphered segment. Now, this whole thing can be written by using some standard symbols. Now, the rounds we will be denoting by nr. So, nr is the number of rounds, and as I have said, the key is k and these are the round keys. Then, as I have explained, g is the round function, and here I put a particular symbol. Instead of x, I will write w to the power 0, which is the input to the first round, then w to the power 1, that is the input to the second round, and so on. So, this is what I have written over here, which I have explained already on the blackboard. Now, what about the rth round? what is happening in the rth round. In the rth round, in the first round what is going in? W0 is going in the second round W1 is going in. So, if I am considering the rth round, then W r minus 1 is going in. In the first round, what is the key? It is K1. In the second round, it is K2. So, in the rth round, the key is Kr. So, the round function G is going to process W r minus 1 comma Kr, and it will produce Wr, and that is what I have written here. So, this is the input to the next round. We will keep on doing this for NR rounds, and eventually we will arrive at the final ciphertext. These steps are formally represented in this slide over here, that is x first W0, then how W1 is constructed, how W2 is constructed, so on, and ultimately how WNR, which is the ciphertext, is constructed. Now, this NR has to be decided by the designer, that how many rounds we are going to apply the function G successively over a plain text and with a sequence of round keys. That has to be done by the designer. For decryption, we have to take care of one point when we are defining the round function, which is this one, that the round function G should be such that G inverse G of Wy comma y has to give me W. Suppose y is the key. So, if y is the key, suppose I have computed the image of W with y, and suppose I want to compute back W, I can do that by applying G inverse over this thing, and I will get W. So, this is a very important condition that a round function has to obey in order that a block cipher is practically useful or meaningful. So, if you look at this sequence of steps, you will see that this is how we decrypt. We had WNR and we apply this property over and over again, and from that we will have WNR minus 1, and then the next step we will have WNR minus 2, and eventually we will have W0, which is equal to not y, but it is x. So, here is a correction in the slide. In the last line, W0 goes to x and not W0 goes to y. Okay, please note that. I will update the slide when when we upload all the slides. Coming to block ciphers in general, when block ciphers are used for cryptography, then they are used according to certain modes of operations. We will discuss 4 important modes of operations right now. The first one is called electronic code book mode, or in short ECB mode. This is the first one. This is the easiest possible mode where the plain texts are segmented into blocks, and these blocks are x1, x2 and so on. So, we have x1, x2 and so on, and we choose a key which is fixed, and each time I am using the encryption function with the same key. Let us say this time on x1, so I am getting y1, this time on x2, so I am getting y2 and so on. This is called the ECB mode. Next we have the cipher feedback mode, in short CFB mode. In CFB mode we introduce something called an initialization vector, in short I0, and say y0 is equal to that initialization vector called IV, and we say that y0 is equal to IV, and we compute z, zi, which is ek y I minus 1, where I starts from 1 and increases. So, if I equal to 0, we get, let us say not I equal to 0, but if I equal to 1, then we get z1 is equal to ak y0. Y0 is a public vector which is the IV initialization vector. So, I get this, and then z2 for I equal to 2, z2 is ek of y1, and I have to calculate y1 once I know z1. So, y1 is x1 plus z1. So, here from E0 I will know z1. Once I know z1, I sum, that is I take the XOR bitwise XOR with x1 and z1, and I get y1. Once I know y1, I will get z2, and so on I will keep on encrypting. So, this is the ciphertext feedback mode, and two last modes are like this, that is cipher block chaining mode, where I start with a initialization vector and then add that initialization vector bitwise modulo 2 to the message, and then apply the encryption and construct yi. Again this yi will be pushed into this, and so on. And output feedback mode is where we start from an initialization vector and then keep on generating these z sub i's by applying successively over the results, and then add the z i's to x i's and generate yi. So, these are the 4 important modes of operations of block ciphers. So, summing up, we started with product ciphers in this lecture. After that we studied the general principles and designs of block ciphers, and then at the end we have talked about the modes of operations of block ciphers. This is all for this lecture. We will study block ciphers in more details in the subsequent lectures. Thank you.